Now question number 6, you please listen. For a reaction taking place in 3 steps at same temperature, the rate constants are Ka1, Ka2 and Ka3, and overall rate constant K is equal to K1, K2 divided by K3. If EA1, EA2 and EA3 are 40, 50 and 60 kilojoule per mole respectively, the overall energy of activation EA is dash kilojoule per mole. This question says about a chemical reaction which takes place in 3 different steps at same temperature. The rate constants of the individual steps are given as Ka1, Ka2 and Ka3 respectively. Their respective energy of activations are EA1, EA2 and EA3. We need to calculate energy of activation of the overall reaction. According to Arrhenius equation, rate constant of a chemical reaction K is related to its energy of activation and temperature as K is equal to A into E raised to minus EA by RT. Here capital A is a constant called Arrhenius parameter. EA is the energy of activation of the reaction. R is the universal gas constant and T is a temperature in Kelvin. Therefore, for the first step, rate constant K1 can be expressed as K1 is equal to A1 into E raised to minus EA1 divided by RT. And for the second step, K2 is equal to A2 into E raised to minus EA2 divided by RT. And for the third step, K3 is equal to A3 into E raised to minus EA3 divided by RT. Now we can represent this equation as equation number 1 and this one as 2 and this is equation number 3. Then multiply equation number 1 and 2 and divide it by equation number 3. We will get K1 into K2 divided by K3 is equal to A1 into A2 divided by A3 into E raised to minus of EA1 plus EA2 minus EA3 divided by RT. Now by adding the 3 individual steps, we will get the overall reaction. The rate constant of the overall reaction K is equal to A into E raised to minus EA by RT. But the rate constant of overall reaction K is given as K is equal to K1 into K2 divided by K3. So we can write A into E raised to minus EA by RT instead of K1 into K2 divided by K3. Thus the equation becomes A into E raised to minus EA by RT is equal to A1 into A2 divided by A3 into E raised to minus of EA1 plus EA2 minus EA3 by RT. From this equation, it is clear that energy of activation of the overall reaction EA is equal to EA1 plus EA2 minus EA3. That is, EA is equal to EA1 is given as 40, EA2 is given as 50 and EA3 is 60. By calculating this, the energy of activation of overall reaction is equal to 30 kilojoule per mole. So here the answer is 30. Question number 7. NO2 required for a reaction is produced by decomposition of N2O5 in CCl4 as by the equation 2N2O5 gas gives 4NO2 gas plus O2 gas. The initial concentration of N2O5 is 3 moles per liter and it is 2.75 moles per liter after 30 minutes. The rate of formation of NO2 is X into 10 raised to minus 3 moles per liter. The value of X is dash. In this question, the equation for the dissociation of N2O5 is given as 2N2O5 gas gives 4NO2 gas plus O2 gas. Here the coefficient of N2O5 is 2, NO2 is 4 and that of O2 is 1. Now we can write the rate of reaction in terms of both reactants and products. That is, rate of reaction R is equal to minus 1 by 2 into change in concentration of N2O5, that is delta of N2O5 divided by delta T, is equal to plus 1 by 4 into delta of NO2 divided by delta T is equal to delta of O2 divided by delta T. Now we can write the rate of reaction in terms of concentration of N2O5 because its initial and final concentrations are given. So R is equal to 1 by 2 into delta of N2O5 divided by delta T. Here the final concentration of N2O5 is given as 2.75 and initial concentration is 3 and the time taken for this change is 30 minutes. Therefore, rate of reaction R is equal to minus 1 by 2 into minus 0.25 divided by 30 moles per liter per minute. So, the rate of reaction R is equal to 1 by 240 moles per liter per minute. Now, the rate of reaction in terms of NO2 is R is equal to 1 by 4 into delta of NO2 divided by delta T. Therefore, the rate of formation of NO2, that is delta of NO2 divided by delta T, is equal to 4 into rate of reaction. Here rate of reaction is 1 by 240 moles per liter per minute. Therefore, it is equal to 16.66 into 10 raised to minus 3, which is approximately equal to 17 into 10 raised to minus 3 moles per liter per minute. So, here the answer is 17. Question number 8. The rate of first order reaction is 0.04 moles per liter per second at 10 minutes and 0.03 moles per liter per second at 20 minutes after initiation. Half-life of the reaction is dash minutes. Given that log 2 is equal to 0.3010 and log 3 is equal to 0.4771. In this question, the rate of a first order reaction at two different times, that is at 10 minutes and 20 minutes, are given. We need to calculate half-life of the reaction. Listen here. When T1 is equal to 10 minutes, the rate of reaction R1 is given as 0.04 moles per liter per second. We know rate of a reaction is equal to a constant K into concentration of the reactant. Therefore, R1 is equal to a constant K into concentration of the reactant capital R1. Then substituting for R1, the equation becomes 0.04 is equal to K into capital R1. This is equation number 1. When time T2 is equal to 20 minutes, the rate of reaction R2 is given as 0.03 moles per liter per second. Then R2 is equal to K into concentration of reactant capital R2. Then substituting for R2, the equation becomes 0.03 is equal to K into concentration of R2. This is equation number 2. The equation number 1 divided by equation number 2 gives concentration of the reactant R1 by R2 is equal to 4 by 3. We know for a first order reaction, the rate constant K is equal to 2.303 divided by T into log R1 by R2. We know R1 by R2 is 4 by 3 and the time for the reaction is 10 minutes. Then the equation becomes K is equal to 2.303 by 10 into log 4 by 3. That is K is equal to 2.303 by 10 into log 4 minus log 3. Here log 4 is 0.6021 and log 3 is 0.4771. Therefore, the rate constant K is equal to 2.303 divided by 10 into 0.1250 is equal to 0.02879. We know for a first order reaction, half-life period T half is equal to 0.693 divided by K. Then substituting the value of K, we will get T half is equal to 24.07 minutes, which is approximately equal to 24 minutes. So here the answer is 24. Now question number 9. R is equal to K into concentration of A for a reaction. 50% of A is decomposed in 120 minutes. The time taken for 90% decomposition of A is dash minutes. In this question, the time taken for the 50% decomposition of a first order reaction is given. We want to calculate the time required for its 90% decomposition. Here the rate of the reaction is given as R is equal to a constant K into concentration of A. Here the power of concentration of A is 1. So the order of reaction is 1. Here half-life of the reaction is given as 120 minutes. We know for a first order reaction, the time taken for the reaction T is equal to 2.303 by K into log R0 by RT. Here R0 is initial concentration and RT is the final concentration. So the time taken for the 90% completion T 90% is equal to 2.303 divided by K. K is equal to 0.693 divided by T half. Here T half is 120 into log initial concentration, we can take it as 100. Then after 90% completion, the final concentration becomes 10. Log 100 divided by 10 is equal to log 10. We know log 10 is equal to 1. Therefore, the equation becomes T 90% is equal to 120 divided by 0.3010. It is equal to 399 minutes. So here the answer is 399. Now question number 10. Integrated rate law equation for a first order gas phase reaction is given by, in bracket, where Pi is the initial pressure and Pt is the total pressure at a time t. Option number 1, K is equal to 2.303 divided by T into log Pi divided by 2Pi minus Pt. Option number 2, K is equal to 2.303 divided by T into log 2Pi divided by 2Pi minus Pt. Option number 3, K is equal to 2.303 divided by T into log 2Pi minus Pt divided by Pi. Option number 4, K is equal to 2.303 divided by T into Pi divided by 2Pi minus Pt. In this question, it is given that initial pressure of a gaseous phase first order reaction is Pi and the final pressure is Pt. We need to derive an integrated rate law equation for calculating rate constant of reaction. Here we can consider a basic gaseous phase first order reaction, which is A gas giving B gas plus C gas. Here the initial pressure of A is given as Pi, then the pressure of B and C are 0. Then after a time t, suppose the number of moles of A reacted is equal to x, then the final pressure of A becomes Pi minus x. Then pressure of B becomes x and that of C is also x. Therefore, total pressure becomes Pi minus x plus x plus x, that is equal to Pi plus x. That is the total pressure after a time t, Pt is equal to Pi plus x. Therefore, x is equal to Pt minus Pi. Now we can calculate the final pressure of A, which is Pi minus x. Pi minus x is equal to, substituting for x, it becomes 2Pi minus Pt. So this is the final pressure of A and the initial pressure of A is Pi. We know that for a first order reaction, rate constant K is equal to 2.303 divided by T into log initial pressure divided by final pressure. Here initial pressure is Pi and the final pressure is 2Pi minus Pt. So here the answer is option number 1.